Welcome to day 4 of the Data Science Fellowship Program, session 11. Today we're going over how to leverage the multi-epoch imaging coming off of wide-field imagers like the LSST. LSST is a time domain survey, and we're going to have many observations of the same part of the sky. The sky is not static. There are supernovae exploding and asteroids whizzing by. And on top of that, the terrestrial sky is changing too. The transparency of the atmosphere is changing, the PSFs are changing. So how do we account for all of these terrestrial factors to best extract the maximum amount of information from this imaging set? And we do this with two methods. We do image addition in order to go deep, and then we also do image subtraction in order to find out what's changed. So we're going to talk about coaddition first. Those of you who are familiar with photography know that taking images at night, it's tough because it's very difficult to make out faint objects. So we increase the exposure times to get more photons hitting our film or more photons hitting the detectors of our digital cameras. I did not just change the stretch or the brightness of this photo. If I were to do that, it would simply look noisier. There is no amount of post-processing that I could do to this photo to make the stars appear in it, for example. There just simply is not enough signal to noise. The signal to noise ratio increases with square root of the exposure time. So if we want to go deeper with our telescope, we just increase the exposure times, right? Wrong. There is a limit to the exposure times you can do in astronomy in practice, and this is because of a number of reasons, including detector effects like CCD saturate. The goal is to get dynamic range, and there's just simply a cap to that. The number of cosmic rays hitting your detector also increases proportionally to the exposure time. And even if there weren't those effects, the sky is not static. There are asteroids whizzing by. In this example, we have a few observations from HSC, and if we had not taken many individual exposures, these asteroids would have looked like streaks in this mean coad on the left-hand image. And if they appeared as streaks, we would not be able to measure their characteristics, like their brightness or their colors. So in this image, we have two coads. That is, we've taken a number of images and then accumulated them. On the left-hand side, we used a mean, which is not a robust statistic, which is why the asteroids still appear in it. On the left, or on the right, we used a robust coad. You can pretend it's a median, but it's actually not. We can talk about how I made this in more detail during the artifact rejection stage. As another example of a reason to take many short exposures are satellite trails. So in this example, you see this image floating around Twitter recently. This is 17 30-second exposures of the comet Neowise, and this image is a mean coad. That is, it did not use a robust statistic. If you had made a robust coad, like a median, for example, the satellite trails would have been completely removed. Not a problem. So the photographer totally did the right thing by taking many short exposures, because otherwise, if he took one 8-minute exposure, the satellite trails would have been impossible to remove. So, okay, so many short exposures are good because of satellites and transients and saturation. So why don't we just take thousands of 1-second exposure? There's downsides to that as well. There is finite readout time and also data volume considerations. The more images you have, the more disk space it takes. And any of you who have been to a telescope know that the readout time can be infuriatingly slow. So disk space has been getting cheaper over the years, and readout times have been getting faster over the years. For example, LSST is going to achieve 2-second readout time because of its 3,000 amplifiers. But still, at 2 seconds, it would not make sense to have 1-second exposures. So there are trade-offs, but the trends are pointing us towards more shorter exposures than in the past. And the LSST, with its thousands of 30-second exposures, is going to have no problem removing things like these Starlink satellites. And other people are catching on as well. Remember this long exposure time image? This is actually a coad that I took with my cell phone. So a lot of cell phones these days have a Coaddition feature where you point it at something and take a picture, and it takes many very short exposures and then coads them together for you at the end. This was taken with Google Pixel's feature called Night Sight, but I think iPhones have this as well, and that's called Night Mode. Okay, so in astronomy, what do we use coads for? They're used for detection, measurement, templates for the static sky, for image subtraction. Before we go into how we use coads, let's take a step back and discuss how we build a coad. Subtraction. Okay, so I'm briefly going to go through how to build a coad in practice. What are the steps? The first step is to define a coad projection and geometry. And I'm going to go through each of these steps in a little bit more detail. Then you have to normalize all the terrestrial differences. There's your WCS, your astrometric calibration. You also have to normalize your photometric calibration. The transparency of the atmosphere is constantly changing. The background levels like air glow and moonlight are constantly changing. And then once you have normalized all these factors out, then you go and take some statistic and collapse your many images into one. In a little bit more detail, there are choices for each of these steps. The first step is defining your output coad geometry. You have to decide what projection or what WCS your output coad is going to have. There's a couple different choices. You can use stereographic projections that have no local shape distortions. You can use equal area projections that conserve surface brightness, which are both good for different things. You have a choice in your pixel scale. The more pixels, the smaller your pixels, the better the image quality, but also the more disk space your image takes. Also remember that smaller pixels isn't necessarily better, given that we're talking about ground-based astronomy where we're limited by seeing usually. Given that there's a minimum full width half max that your telescope can achieve, you don't necessarily gain anything by going to super tiny pixels. And finally, your last choice is how big are the images going to be? Like, what is your unit of coad, or how many pixels is your FITS file going to have? There's a few different choices here too. Different projects have used different tessellations. HyperSuPrimeCam uses this one called the Rings sky map. We've also thought about using much bigger images as well, like a dodecahedron. Right now, the baseline is the Rings sky map. the so the image with a constant WCS we are calling a tract, and that gets subdivided into smaller regions we call patches. The trade-offs here are that if your tracts are too big, you have distortions at the edges. If they're too small, remember you have to overlap on the edges. The cost of storing those overlap regions increases, so you can't have arbitrarily small tracts. Okay, once you've decided on your output geometry, you've already done your astrometric calibration and have the WCSs of each of your input images. The first step is to warp or resample all these visits onto this coad geometry. This is a convolution, which makes it an expensive step. Every time you move a window on your laptop, for example, or grow it or shrink it or rotate an image, your GPU is resampling it onto your display's pixel grid. There are a number of different choices of warping kernels that you can use. We are using a Langshos 5. A Langshos infinity kernel, it would be the same thing as a sync kernel. The Langshos kernels are just a properly truncated version of the sync kernels. If you want to read about this, I grabbed this image from this paper. Okay, once you have resampled to a common grid, that is a star that lands in one pixel in one image, lands in that same pixel on every other image, you can now scale to a common 0 point. The transparency of the atmosphere not only varies with time, it also varies spatially as well. So this is where you use your photometric calibration to basically scale each one of your input images to a common flat 0 point. This is a multiplicative factor. The third step is to handle your additive effects. You'll remember in the detection and background subtraction talk that the additive effects are both background, like air glow and moonlight, but also other sources. And in this case, artifacts that we want to remove. That is transients like supernova that we want to show up in the difference images rather than the templates of the static sky. These also include asteroids, ghosts, any temporal effects that we want to remove. So these are two algorithms that I have worked on personally, so I'm going to avoid discussing them for now, but if you want to hear more about them in the live session, I would love to tell you more about them. And then the final step is actually stacking these pixels now that they have been normalized, and now each pixel basically is drawn from the same distribution. This we go into more detail in the notebook. Now that we have built coads, how are we going to use these coads? We want to use coads for detection, for templates for subtraction, and even for measurement. That is, flux measurement or shape measurement. And for both of these, but especially shape measurement, having a PSF model is very, very important. So what do we do about the PSF of this coad? So one thing that people do is they generate a coad of the PSF models. We're using the same weighting as the same weighting of the visits that were used in the regular coad. But you'll see that there are downsides to this too, mainly that there are discontinuities in this type of PSF. On the left is a coad with roughly 30 visits, and on the right is a map showing the number of visits that have contributed to each pixel. So in the dark regions, there's roughly 25 visits that have contributed. For the white regions, roughly 33 visits have contributed, and what you're seeing is all the chip gaps of the original input images lining up. And these chip gaps give it a plaid look. In addition to the chip gaps, you can also see where the artifacts were clipped too. There's satellite trails going through it, and you can see some ghosts and asteroids that were clipped as well. So imagine that you have a star that falls on one of these chip gaps, where half of the star has had, for example, 10 visits contributing, and the other half of the star has 11 visits contributing. The PSF on one half of the star is different than the PSF of the other half of the star, which makes this very difficult to measure. So one thing that people do to mitigate this is to build coads per object. That is, build a coad of this star with just the 10 visits, leave out the 11th because it can only do harm. And we refer to these as per object coads or cell-based coads, because you can do it by blocking up this coad into little cells as well, and make multiple coads of each cell with just the number of visits that are required to measure certain objects. So everything that we've talked about so far are on direct coads, meaning we have not done any kind of convolution to these images other than the warping or resampling. There are other ways to get around this discontinuous PSF problem that involve extra convolutions, but there are trade-offs involved with these as well. So these flavors are PSF matched coads, wherein you can match the PSFs to a model PSF. And this is actually how we do image subtraction, and we'll talk about this in more detail in the second half of this talk. You'll remember in the detection talk, we generated detection maps or likelihood images before thresholding, and this was done by correlating the image with the PSF model. Now, you can coad these detection maps and make a total complete detection map, because remember that adding log likelihoods is the same thing as multiplying likelihoods. However, these would be good for detection, but are very unwieldy for measurement because of all the uncorrelated noise. In theory, you can decorrelate this noise after coaddition, and this result was published in 2 papers, one by Kaiser, one by Zake. They claim that this is an optimal coad, but remember from before, whenever anybody says something's optimal, you ask what are the assumptions and conditions under which this is optimal. And this is only optimal in the case where the PSFs are not spatially varying and the input noise is also not spatially varying. This holds for Fourier methods in general A lot of people new to astronomy will ask why we use convolutions in pixel space when we can just do a multiplication in Fourier space. And the answer is that with real astronomical data, there are masked pixels. There are saturated pixels that you need to avoid. There are contaminated pixels you need to avoid. The PSFs are not spatially constant, and the noise isn't spatially constant either. Like all these assumptions break down. And so while you can do Fourier transforms of little small thumbnails where you can assume that all these assumptions, where you can assume that these assumptions are true, you don't get the same performance gains from doing this on the whole image because it's just not robust. Okay, and finally, another flavor of coad, which has nothing to do with extra convolutions, is to go even deeper, you can combine the imaging from all your different bands. So far we've been talking about building a single band coad, so like coadding all the I band images or coadding all the R band images. You can coad all the bands combined using a weighted sum of the per band detection maps. And the optimal weighting of the different bands depends on the SED of the object that you want to detect. It would be unwieldy to do this for every type of astronomical object that we can think of. And also, we don't want to bias the detection to particular types of objects. So the way around this is to build one that is optimal for the SED of the sky, because it frames detection as rejecting the null hypothesis of the pixel sky. And we call this the chi-squared coad. We can also use these templates. We can also use these coads as templates for image subtraction. We do image subtraction in order to find what has changed in the current observation. It is very difficult to pull up two different images and play the game of where's Waldo to see what has changed. You really have to blink the images or subtract them. In the past, with photographic plates, this was done with a mechanical device called a blink comparator, and this is how Tombaugh found the trans-Neptunian object that we named Pluto. Nowadays, if you want to pull up two images and see what's different, usually you just open them in DS9, match their frames, and then use the blink feature. Image subtraction is a way to do this automatically. In general, we perform image subtraction by taking a template and subtracting it from the science image to subtract away everything that has stayed constant and reveal only what has changed. Then you can run detection on this difference image to find just the differences. Previously, when generating coads, we talked about how we had to match the 0 points, the WCSs, the backgrounds, but it wasn't critical to match the PSFs at this point. You could generate a coad with different PSFs per observation. However, when it comes to image subtraction, it is time that we have to handle the PSFs that vary both spatially and temporally. We do this by PSF matching. What this problem comes down to is we want to find the kernel that we need to convolve the template with in order to reproduce the PSF of the science image. That is, we want to convolve the template and have the output convolved template have the exact same PSF of the science image, that when we subtract them, the stars subtract cleanly. So in the history, there is some history for methods to do this. In the 90s, people computed a convolution kernel in Fourier space, degrading the resolution of the worst seeing image. However, working with this in Fourier space is the assumptions that you need in order to do that do not hold. The PSFs are varying spatially, the noise is varying spatially, and there are discontinuities and really, really sharp features like cosmic rays and masked pixels that kind of blow up the noise when you work in Fourier space. So this was a problem. In '98, Allard and Lupton modeled the convolution kernel as a series of basis functions. This was robust and allowed for spatial variations in the PSF. You could actually solve for this kernel using least squares. However, that made the assumption that the image noise, or rather the noise in your template, was much, much lower compared to that of the image. It was basically in the limit that the template is noiseless. This was implemented by Andy Becker as the code he called Hot Pants. This is also what he implemented in the LSST science pipelines as well. In 2016, Zake recognized that this is not optimal if the template is noisy and proposed an alternative, which we call Zogi, after the author's initials. This has the nice properties that it's symmetric between the science and template images. However, it did return to working in Fourier space, which was a no-go for working with real astrophysical images, because it again requires no discontinuities and exact knowledge of the PSF, which we astronomers do not have. What we ended up, however, we were able to extract the decorrelation step. Basically, what we were able to do is produce a hybrid of these two methods. We still do the convolution kernel in real space. However, afterwards, we can extract a piece of the Zogi algorithm which decorrelates the noise and normalizes the noise. If it seems like I glossed over this, it's because I did. If you want more information, please watch Jean Manier's talk that he gave at the LSST Algorithms Workshop earlier this year. Also see Robert Lupton's talk slides at the Project and Community Workshop last year. And you can also, if you're curious about what exactly we're doing in the science pipelines right now, please see Eric Bellum's talk. Okay, so that's how we make image differences in theory. What do these look like? So here's a few CCDs from Hypersuprime Cam again. And these are difference images, and you see a lot of stuff in them. We see some ghosts, basically all the artifacts that we were talking about rejecting during the coads now appear in the difference images, plus extra. We have ghosts and satellites and cosmic rays, and a bunch of other stuff. Looking at this a little bit more closely, it's important to be realistic when you look at your difference images. This may look kind of busy, but you have to really compare it to what the science image looks like and what the template looks like. And when you look at what appears in the difference image, it really is just the very bright saturated stars from your template. And there's an exercise in the notebook that explains why this is. Basically, you will never be able to remove all the bright saturated stars. It is simply impossible. So this is actually looking pretty good. Zooming in on a different CCD, we see we've got a couple very bright stars, a cosmic ray, not sure what's going on with this galaxy, another cosmic ray. This is looking pretty beautiful. This other difference image, we've got another saturated star here, but other than this dipole, all I see is noise. Gorgeous. A little note about dipoles. So what we've been looking at is HyperSubPrimeChem data. HyperSubPrimeChem has an atmospheric dispersion corrector. The Rubin Observatory will not. The atmospheric dispersion corrector corrects for differential chromatic refraction. The atmosphere bends blue light and red light differently, such that if you were to look at an object in the sky, you'd see a little like blue rim on the top and a little red rim on the bottom. And this is because the actual positions of the red light and the blue light are shifted. So PSFs are in fact chromatic. The PSF of an astrophysical source depends on its SED. So if you have dipoles, the way you can tell if your problem is differential chromatic refraction, and these are a series of dipoles that were detected in some DCAM imaging. And they're roughly oriented the same way. However, some of them have the positive node in the top left, like this one, this one, this one, and then others have the positive node in the bottom right, like these. And this is because the polarity flips depending on what the color of the star is. For the Rubin Observatory, we're going to be handling this with software. One way to do this is to manage the PSF models as chromatic objects, and another way is to correct for the differential chromatic refraction when generating the coad templates. For more information about how to do that, take a look at Ian Sullivan's talk at the Algorithms Workshop earlier this year. All right, when we looked at what was left over in the difference images, we could see with our eyes the bright stars, the cosmic rays. But remember, with the bright stars, while they may take up all of your, they may be all that you notice, but number counts decrease as a power law as brightness increases. There's many more faint objects than there are bright objects, and so your false positive rate on difference images, that is your detections, your false detection rate, will always be dominated by noise in the faint end. The reason for this is if you have two random Gaussian fields, PSF match one to the other, and there's nothing in this image, it's just pure noise. Subtract one from the other, correlate with the PSF, and then do detection. The false positive rate predicted is given by this equation and shown by this orange line here. This means that even if there's nothing in your image, you will still have detections in it, just from fluctuations in the noise. So this is why it is critical that you have an accurate noise estimate when you're doing detection. And in fact, one thing you should do when you are checking your difference images is just plot up a histogram of the signal to noise ratio of your sources that you've detected on it and see if this is roughly in the vicinity of your expected counts from the noise. Just as an example of this going wrong, this was just a one-off experiment that I had done while I was checking a new type of template. And there's the noise is estimated 3 different ways on these images. Here, the positive detections are shown in dark blue, the negative detections are shown in cyan. The image on the left is a difference image with that extra Zogi decorrelation function turned off. On the right, it was turned on. On the top, I used an empirical noise estimate, and on the bottom, I used the variance plane noise estimate. And you can see just by changing these noise estimates, on this left-hand side, the entire image is a detection. Clearly, problem with the noise here. And on the right hand, this image, I see a lot of stuff here that was not detected. Also indication that there's a problem. And then this image looks just right. So this not only shows how critical the noise estimates are, I recommend that if you are getting strange detection rates on your difference image, take a look at what's being detected, and there's a good chance that your noise estimate is what is causing problems. So now we've run detection on these difference images. What do we see? Let's zoom in a little bit and I'll explain what the color-coded numbers are. Okay, so everything that has a marker on it was a detection. If it is a red plus, that means it has been flagged as either saturated, bad, meaning it overlapped a defect pixel. If it's a red circle, it means that when we actually went to measure it, the signal to noise of the PSF flux was less than 5. Orange means that the shape measurement failed on it. And cyan is everything that's left over after filtering for all those problems. And what we see is some blobs of a cosmic ray here, here, here. It's comforting to see that these dipoles were saturated. But the only thing that's really left is maybe this dipole up here, and I'm not sure what's going on with this thing here. So in theory, we could, there would be like a beautiful supernova in one of these pictures, and then we could go follow it up with our big glass. But, okay, so another really fun thing about LSST and running in survey mode is that we are continuously observing the sky. So if we see anything interesting in these difference images, we can go back to the previous observations and see what was there in terms of its colors or the deep image or the light curves. How has that object been changing before? How do we generate light curves? There are some considerations here too. What you should not do to generate light curves is use the catalogs detected on the single epoch image and then match them and generate a light curve of those matched catalogs. The problem with this is that if you have a source that is hovering around the detection threshold. Sometimes it's above the detection threshold and is detected. Sometimes it's below. And if you observe this at those times, and only the observations where it's above the detection threshold appear in your catalog, once you match these and take the mean, your estimate is going to be biased high and your light curve is going to be incomplete. So what we do instead is forced photometry by measuring the centroids on the deeper coads and then forcing PSF photometry at those locked centroids and recording the PSF flux measured there. You can do this force photometry on these single epoch images, and you can also do them on the difference images too. There's of course trade-offs involved with doing force photometry on calyx, the single epoch images, or the difference images. The single epoch images they have lower variance because they've had fewer convolutions that correlate the noise applied to them. However, they are also biased. So in these series of thumbnails from Claire Saunders, she is looking at multiple observations of the same source and then is plotting the residual PSF flux as a function of the seeing of the observation that it was observed in. So for an isolated star, the forced PSF photometry looks pretty constant. The residuals of this look pretty good. However, for blended galaxies or even undeblended galaxies, the PSF flux starts depending on the seeing of your observation. And this is because as the seeing degrades and the seeing changes, the light from the galaxy is more or less smeared out. So the way to remove this bias is to use difference imaging. If you do force photometry on the difference images, the light from the constant galaxies gets subtracted out and no longer contaminates your estimates of the PSF flux. We've taken this pile of multi-epoch images, we've gone deeper by adding them, and detected what's changed by subtracting them. Image subtraction is still an active area of development, looking at these detections on this difference image, which is actually pretty good quality. We see that only a small percentage of these detections are transients that we would want to follow up on. And this has been an area where machine learning has been helpful, since the artifacts, the difference is mostly morphological, and the artifacts are very camera specific, and we don't have good physical models for what these should look like, or predictions for what they should look like. I hope to have shared at least some of my optimism on what a survey made up of many short exposure times over 10 years can do. I am happy to answer questions in the in-person session and look forward to discussing this with you. Thank you.